Hi, everyone. Thank you for being here this afternoon. Before I get started talking about my research, I first want to thank my postdoc co-mentors, Ruth DeFries, Arlene Fury, and Pat Kinney, as well as extend a thank you to collaborators, individual collaborators and institutions that have supported the foundation for the work that I'm continuing in my postdoc at Columbia. The title of my talk is Modeling Air Quality in India, quite broadly defined, but we'll get into specifics moving forward. So in thinking about air quality, in the United States we have the Clean Air Act. Obviously the rest of my talk will be on India, but for now I want to talk about how air quality has kind of played out in the US in terms of regulatory cost, as well as extensive benefits that have come as a result of cleaner air quality. So from the graph on your left, the orange indicates the costs. Air quality regulations in the United States are the single biggest regulatory expense that we have, but that comes with an associated benefit of nearly $20 as a median estimate per every dollar spent in regulatory action. And most of those benefits are derived in the form of hospital visits, reduced hospital visits, reduced respiratory issues, and reduced premature mortality. Doesn't stop there. There are also benefits in the form of ecosystems and agriculture. On the bottom right-hand plot is showing degradation to a watermelon plant due to ozone exposure. Now, this kind of regulatory framework does not exist in India, and there are many instances where pollution across India, or namely in Delhi, the pollution will be so bad that you will experience situations such as depicted in these images. And in fact, most recently in early November, there was a significant pollution event where concentrations of fine particulates less than 2.5 microns exceeded 1,000 micrograms per cubic meter. Now, to put that into context, the US regulates PM 2.5 at an annual average of 12. So it's a quite different experience between what we would consider a polluted day in New York City versus what populations in India deal with on a daily basis. These conditions amount to more than 580,000 lives lost prematurely due to air pollution from ozone and PM 2.5, which has been estimated to amount to about a $640 billion cost to the economy. So moving forward, thinking about, okay, we have a sense of pollution is bad, it has negative impacts on human health, but where does this pollution come from? I've listed, in the form of fun images, 6 different emission sectors where pollution is emitted from, and they come from a variety of sources, including agriculture and natural sources like lightning and volatile organic compound emissions from plants and trees, as well as the traditional pollution from fossil fuel combustion in the name of transportation emissions, power plant emissions, and domestic combustion. Now, the pollution that is directly emitted from these sources are in the form of primary pollution in the leftmost bubble. And I've listed some of the gases and particulates that come from these sources as well. Those pollutants that are emitted into the atmosphere can then react or undergo oxidation or photolysis and form new pollutants known as secondary pollution, which are in the form of ozone and PM 2.5 species, as I've listed here. So ozone is not directly emitted, it is only formed in the atmosphere. But you'll note that PM 2.5 is in both of those bubbles, so it has both primary component and a secondary component, which makes PM 2.5 an complex and intriguing pollutant to study. So moving forward and talking a little bit about the research that I conduct, I wanted to outline first with some motivating questions. And my research is really driven by trying to understand how spatially distinct anthropogenic energy sector emissions, so those transportation, residential combustion, and power plant emissions, vary regionally across the country. And then what do those differences in spatial variation mean for regional air quality as well as human health? Oh, sorry, I got a little funny. But the way that I conduct my research is through a modeling framework. And so I've been using the US EPA's Community Multi-Scale Air Quality Model, which is a three-dimensional model that has various meteorological and chemistry components built into the model, and it requires inputs in order to produce any output. So I've listed some of the inputs that are important for modeling my scenarios on the left-hand side, and those include anthropogenic emissions, biogenic emissions, biomass burning, boundary conditions, as well as meteorology. And when all of those are thrown into CMAQ and the model runs through its several hundred chemical and meteorological equations, we receive some output. And so I've listed some ambient concentrations: nitrogen dioxide, sulfur dioxide, ozone, and PM2.5 that I'm mostly interested in, but there are a number of other factors and like deposition variables and various other tracer species that are also output in this data set as well. So for the time being, I'm going to walk through some results just of PM2.5 this afternoon. So the next couple slides, I'm showing some results from my PhD, where I built the foundation for the rest of my postdoc model using CMAQ over the subcontinent. In my PhD, I also conducted a thorough evaluation of the model as compared to surface and satellite observations. So here I'm showing on the left-hand side, we have a plot of annual average PM2.5 surface concentrations overlaid with surface observations taken from the literature. So immediately what you'll recognize is that we have a high concentrations to the northwest of the domain, and those are from wind-blown dust as introduced into the model simulation. We also notice that there is a strong pollution gradient going from north to south. So the highest concentrations of PM2.5 are in the north, where we have the greatest population density and therefore the greatest emissions. And then you will also notice that compared to those little dots of surface observations, which are not in reality that large of a spatial area, they are one point in space and time. But in order to overlay them on this plot, they just come out a little bit bigger. But you will see that compared to the model, the model compared to the observations exhibits a low bias across the whole country. So in trying to diagnose where this bias is coming from, we can go a little bit further into our PM2.5 composition. And here I pulled out subspecies that make up total PM2.5. So namely, I've chosen primary particulates in the form of elemental and organic carbon, secondary inorganics in the form of sulfates and nitrates, secondary organics, which are secondary organic aerosols that are oxidized volatile organic compounds, and crustal particulates, which are those wind-blown dust components. And this is in itself a really unique way to assess our model performance, but we can also compare with existing observational studies to get a sense of how our model is performing with regards to these subspecies. So in this box, I'm comparing my study, which is this study, and those percent contributions on average at a specific location to comparing those with results from this observational study. And the biggest driver, which I'm going to draw your attention to, is those primary particulates and how I'm estimating about 20% contribution at this location, whereas it's being measured at about 45%. So there's so from this we can see that these primary particulates, which are primarily emitted PM2.5 particles in the form of elemental carbon and organic carbon, are likely underestimated in the emissions inventory. So there are a couple ways that we can address this moving forward in the modeling framework. We can increase the resolution of the model, or we can adjust the to finally resolve maybe urban pollution is being kind of smoothed out in the averaging process, and so we can resolve that a little bit better at a higher resolution, or we can update our emissions inventory. And so I've gone ahead and done both, and I am taking that same emissions inventory, running it through CMAQ at a higher resolution to estimate the health impacts at the baseline. And then I've also updated the emissions inventory for transportation and domestic combustion using specific urban and rural combustion factors, as well as population distribution. And then I've updated the power plants as well, using specific power plant location data. And so from there, I'm able to compare an updated simulation with my baseline to get a sense of how these emissions are affecting the sensitivity of the model to the emissions in calculating PM2.5. And I would like to note that in the future, this work will also include biomass burning, which is a strong contributor to PM2.5 in this region. So these are preliminary results from these simulations, and the top left shows the monthly average concentration of January 2010, or of PM2.5 in January 2010 for that updated simulation. So you can kind of pick out, I mean, if you look really closely, I'm not sure how well you can see from back there, but there's a little bit of structure to the concentrations. If you look towards the southern part of the domain, there are some hot spots of PM2.5 mixed in with lower concentrations. In the bottom plot is the updated emissions simulation, PM2.5 concentrations for July. And I draw your attention to both of these months because they have very different meteorological, it's a very different meteorological environment. So in January, there's a strong inversion layer which traps the emissions and exacerbates the pollution, whereas in July, it's the monsoon season, and so a lot of that pollution is rained out due to the monsoon. Now, the real takeaway from this, though, is on the right-hand side, where we have that percent change between the updated and the baseline simulations. So those are changes introduced solely from including updated information in the emissions inventory to reallocate spatially the transportation and the domestic combustion and the power plant emissions. And so generally, just updating those emissions has a pretty strong impact at the local and the regional level. So now one of the questions I'm interested in understanding is how does this impact premature mortality? And so we can estimate premature mortality due to PM2.5 by taking some baseline mortality, multiply that by an attributable fraction due to that, due to the pollution, and then multiply that by population. On the left-hand side is showing the estimated annual premature deaths for the updated simulation. The right is for the baseline. And at first glance, they look pretty similar, but there's actually across the whole domain, there's actually a 70,000 person difference in estimated premature deaths. And if I draw your attention to specific areas, we can start to see where those differences actually come across. And in fact, just thinking about Delhi, one of the most populated cities in the world, let alone in India, and just updating those emissions shows that the model responds in such a way to produce an exposure that reduces estimates of premature mortality by nearly 3,000 people. So in conclusion, CMAQ is sensitive to these emission locations, which are reflected in just those 3 sectors that I updated in these preliminary simulations, which these sensitivities could lead to under or overestimates in ambient air quality and therefore human health impacts. And finally, including this updated information may be able to reduce some of these biases. So just some ongoing research thinking about how these sectors contribute to urban and rural populations in terms of health impacts. How can we disentangle the effects of meteorology, emissions from various sources, and regional pollution in high pollution episodes, so namely that 1,000 microgram per meter cubed event in Delhi last month, and then how are we able to investigate future emissions versus future climate in the region with regard to health impacts. And so thank you.